Okay, today we're going to study the Young's double-slit experiment. So let's see, we take, for example, two slits. Okay, here is a slit 1, here is a slit 2. And then we take some monochromatic light, which is one wavelength. So here is the light here. Okay, like a laser, like a red laser, for example. Okay, so remember the light is coming from everywhere from the laser. So one ray will hit this slit, another ray will hit this slit. Now, this slit is so tiny, so we have actually diffraction or flaring. Okay, so we put a screen here. Here is a screen. I put here a screen. So one ray will go, there are a bunch of rays, they're going to go different direction, but we just choose one. It's going to go and hit there. Okay? And then we can call this distance R1. And then another ray is going to come out from here. Remember, when it comes out, there are different rays. They go different direction. We choose one that's going that way. And we call this one R2. Okay, remember this is a laser like a red or blue laser or some other color. Okay, so this distance between the screen and the two slits, this we call it L. This distance L. And the distance between the two slits, we call it D. The distance between the two slits, we call it D. Okay? So now, these are waves. So this is a wave here, because light is a wave. And this is also a wave. So these two waves, they're going to interact at that point. They're going to interfere. So we have wave interference at that point. So for the wave interference, you can have many cases. You can have a case if they're in phase, like one wave going this way, the other one that's coming going that way. So these are in phase. In phase. If these two waves are in phase, they're going to add up and we have construction. So I put here construction. And then what you get a bigger wave with bigger amplitude, something like that. This is construction. So now, so we can have a case like this where the waves actually are out of phase. When this one is high, the other one is low. It's like that. Something like this. Okay? They don't have to be, I made them touch because I don't have enough room. So these are out of phase. I put here phase. This is destruction. So actually you don't get anything, because if you think about it, this bump here, okay, will go into this dip here and vice versa. So they cancel each other out and you just get darkness. So this is bright fringe. This is dark fringe. Now, when they meet here. Now, what we can do, we can look at, take some line here from a slit S2. We use different color. And we go like that, perpendicular, like that. So, and then we can say, because you see this L is really big compared to the wavelength. So we can say, for example, that this distance here is this one minus that one. And let's call that distance delta, this distance here. So we can say R2 minus R1 is equal to delta. Okay? This is an approximation. We are assuming that this distance here is way big compared to the wavelength. Okay, and that's true because the screen usually is like 4 meters, and the wavelength is really so small of the laser. Okay, so you can make this approximation, and you can say that I can put here some angle theta, and you can say that sine theta is equal to the opposite, which is delta. I put here delta over d. This is d, and this will give me delta is equal to d sine theta. Now, what we need to do after this, we look at this delta. This delta, it can be, for example, a multiple of wavelengths. So I put here delta is equal to m lambda. So this m that I have, it can be 0, 1, 2, 3, okay? It can be -1, -2, that m. Now, if you have this delta is happens to be equal to some multiple of lambda, you have a construction. Why? Because this is, try to follow me carefully because this is tricky. Let's see if we have only delta is equal to, let's see if m is equal to 1. We have only 1 lambda. Now what's going to happen when at this point here, this wave is going to be behind this one by 1 lambda. So the next wave of this one will meet the next one, the wave of this one, in phase, because the difference is lambda. Let's see, for example, you have some wave that's traveled like this. Here is a wave. And let me look at here. This is one wave. We have 2 wavelengths. We have this one, then we have that one. This is lambda, this is lambda. Now, if we look at some other wave, let me see here, like this one. You can see that this wave has 1 wave ahead of this. And remember, these waves, they keep going, continue. And this wave here is ahead of this wave by 1 wavelength. You can see here, this one has 1 extra here, but this one doesn't. So what happened when you allow this to move, this one is going to encounter that one and it's going to be in phase. You can see this, you have a dip and then you have a crest here. Now, when you have the change of this delta, when it's some multiple of wavelength, the waves will meet and then you have construction. So what we can write, we can say d sine theta, which is here, is equal to delta, but delta is m lambda. And then we have this. And here we put construction. The wave constructs. Now, what does it mean? It means that you have bright fringe. On the screen, you see something like, let's see, we come over here, for example. I'll show you. Like here, we have a construction at this location. The intensity of light is higher. This is the intensity of light. So here we have a destruction. Here, construction, but not as much as the one in the middle there. You see, construction. We have destruction, construction, construction, destruction, construction, destruction. So when the two waves are in phase, you get construction. Where they're out of phase, you get destruction. Now, for destruction, we can say d sine theta is equal. Now, instead of putting m, I will put m plus 1/2. And then I put lambda. So if I add 1/2, I just do a half wavelength, add to a wavelength, then I will get destruction. Let's see how I can explain this. So let's see. Here is a wave. It's coming out to the door. Here is the door. I put door here. Now, the other one is behind this one by half wavelength, which means looks like this. Let me see if you see when I have this bump here, I have a dip here. So now what's gonna happen? The difference between, and these waves, they keep going, and this one also keep going. But this one is ahead of this one by half wavelength. This is lambda over 2. So when this one comes to the door, here is the door, this one. When this one comes to the door, it's gonna be like that. But this one is gonna pass, it's gonna be here, and this one is gonna join there. So you see this one here meets that one. So this bump meets this dip, and then they cancel each other out, and then you get flat outcome, and this is destruction. They destruct. So you get a dark fringe. I put here destruction. Okay. So when you shine this on some screen, you get some on the wall, for example. You get some spot, some fringe that looks like this. Let's pretend we have a red color. So you're gonna get a red fringe like this. And then next to it here, you get small one like that. This is on the wall. I put here wall. On wall. And here, a red spot like that. And here, it's tiny, smaller. And here, smaller. So this bright fringe in the middle is this one. This dark fringe here is this one. This bright fringe here is that one. Okay? So you get in bright, dark, bright, dark, bright, dark. Keep bright, dark. So that's what you see on the wall. Now, if we go to here where we have destruction, where we have construction, that's sine theta. You see this sine theta is actually small because this delta is really tiny. So we can make an approximation. Let me do this. And we can call that angle theta. Okay? We pretend that these two, because like a rubber band you stretch and it's to long distance, they're going to become parallel. So pretend like these two are parallel. If these two are parallel, this theta here, this angle, will be equal to that angle there. Okay, and let's call this distance here from the center to the fringe, or to the point where the two lights meet, we call it y, and we have L here. So theta is small, so I can put here, I can put theta small, theta small. If theta is small, we have this, we can say sine theta is approximately equal to tangent theta, because theta is small. Sine theta is equal to tangent theta. And we come over here, and instead of putting sine theta, I put a tangent theta. So I come over here, I put d. Instead of putting sine, I put tangent. Tangent theta is equal to m lambda. Now, I took this. Well, we need to know why sine theta is equal to is approximately tangent theta if theta is small. If theta is small, you're going to get cosine theta is 1. Tangent theta is sine over cosine. Cosine 0 is 1, so you get sine theta is equal to tangent theta approximately. Now, tangent theta, look at here, the angle theta is equal to the opposite over the adjacent. The opposite y, the adjacent is L. So I put here d, and then I put y over L is equal to m lambda. And look at this equation. Let me box it in red. This equation is very, very useful. Okay? Because you can bring some laser beam that you don't know. For example, some light, some ray that you don't know, monochromatic light that you don't know its wavelength. So what do? You give it 2 slits, do the interference, and then you want to know its frequency, because if you know lambda, you will know the frequency. Lambda is c over the frequency. You know the speed of light, so you can know the frequency by knowing lambda. So how are you going to know lambda? Why is you just go and measure from here. Let's see, you want to go from here, measure from here to this. Okay, for this is, well, let me go bump, make a bump here. And this is m is equal to 1 here. So I measure from here to here, that distance, and that will be y. So I know y. This d is the distance between the 2 slits, which you know already. This L is the distance between the screen and the 2 slits. L is known, y is known, d is known, m is 1 for the first fringe. Okay, this one. So m is 1, and then you can find lambda. You can find the wavelength of that beam, or of that ray. Okay. So this equation here is useful, and it comes from the interference of light.